Hey, John here. Let's look at what we call a binary search. In the situation where you have an array, and we're going to consider an array in this case. There's other data structures you can do this with. It turns out it's most convenient to do this with an array. Let's assume we have an array that's already sorted. This only works on a sorted array, okay? What do we know? We know how many elements that we want to look at in our array. The first array element starts with 0, and the last element number is the number n minus 1, right? So let's put a index with a value of 0, representing the low end of the set of elements we want to search in, and we're going to put another index at the high end, not n, which would be over here. You're not going to set this one to 6. You're going to set it to n minus 1, okay? So this is the first element through the last element, inclusive, where we want to be doing our searching. Let's say we want to search for the card who's number 7, okay? Well, in this scenario, what we're going to do is we're going to take advantage of the fact that it's sorted, and we're going to actually search it like you would a phone book or a dictionary or something like that. If you actually have seen one and used a real one before, you kind of, if you're going to look for something, you kind of open it in the middle and you kind of give an eyeball and you say, well, let's say I'm looking for, Mabel or something like that. And you open up the dictionary and you end up looking at Olive. Well, you know that Mabel must come before Olive, so you kind of then start looking towards the front of the dictionary and so on. But if you're looking for Smith, you start at Olive, you need to go the other direction. And you're not going to read, my point is, you're not going to do a linear probe. You're not going to read the entire dictionary looking for zebra. No, you're going to start near the end. Now, how do we automate this thing? The computer is not really good with intuition, so what we're going to do is we're going to just brute force this thing. This is what a binary search really is, okay? So if we know the first and last element, what we're going to do is we're going to check the middle first, okay? And we're going to define the middle as the low end. We're going to call this the low and the high index. We're going to add low plus high and divide it by 2, all right? This is 5, right? 1, 2, 3, or 0 rather. 1, 2, 3, 4, 5. Okay, so that's 0 plus 5 over 2. We're doing an integer division here, which means you take the quotient and you take the floor of that. So 5 divided by 2 is 2. And we're going to put this mid pointer right there. All right, remember we're looking for the 7 here. So we're going to start in the middle. We calculate the mid. We say, is the element at the middle the one I'm looking for? Does that equal 7? No. But I know I need to look to the right. Remember, this is sorted. It only works on sorted. So we don't need to look over here. Don't even need to look there. We throw that away. We throw half, logically speaking. We're going to throw half this deck away in the very first search. So if we know it needs to be on the right, what we're going to do is we're going to move the low pointer over here, and we're going to do that. We're going to set it to this mid plus 1 because we already checked the mid. We know it's not there, and we know it can't be over here. All right, and we start over again. We say, look, is this low pointer, the index is the low end, still less than or equal to the high index? And as long as that's true, we have more stuff to look for. All right, we'll see this in a second. So we're going to calculate the midpoint, right? Well, what do you got? 1, 2, that's 3, 4, 5, plus 5, that's 8, divided by 2 is 4, right? So now this will be index number 4. As you can see, it came out right this time. It depends whether you got an even number of elements or an odd number of elements. The rounding only applies if you end up with an odd number, right? So anyway, then we execute our question again. We say, is this the card we're looking for? And it turns out we were looking for a 7. The answer is yes, we're done. We found that by comparing 2 elements. Okay, we didn't check all 6. We only looked at 2 in this scenario. That's a good gain. All right? Let's say we weren't looking for the 7. Let's say we were looking for 6. What would happen here? Well, then that would not be the one we want. In this case, we would say, well, it must be on the left of this thing, right? Well, we're not going to move the low pointer over. This time we're going to move the high pointer down, right? Where are we going to move the high pointer? Well, we know it's not this. We know it can't be over here. So we're going to move the high pointer to the mid -1, much like we did with the low pointer. Now they're both pointing right here. We're going to then calculate a new midpoint, right? Because this is less than or equal to this, right? Remember, our end condition will be when these two cross over, okay? So what's the midpoint when they're both pointing at the same thing? Whatever this is plus whatever this index is divided by 2 is going to be the same value, right? 0, 1, 2, 3 plus 3 is 6 over 2 is 3. So the midpoint will also end up pointing in the same place. Remember I said in this scenario we're looking for the 6, right? Is this the one we're looking for? No, it's not. Is the one we're looking for greater than this? Well, yes, it is. Remember what we do when that's the case. We take the low pointer, set it to the midpoint +1, and we'll end up over here. Okay, then we start over. We ask, is the low pointer less than or equal to our high pointer? The answer is no. Now with only checking 3 items, we know it's not in this list. It should have been between here, okay, but it's not. All right, you can run some other scenarios yourself and ask, what if I'm searching for a 9? What'll happen is what? It's going to say no, then it'll go here just like it did before. Midpoint here, it'll say no, it'll move it over to here. Midpoint will be here, it'll say no, then the low will move over there, and again, they cross over and we're done. So this, you can run the various scenarios and you can see that this works out. Now, it turns out numerically, this is going to run in what we call log 2 of n times, all right? So think about that, right? With our linear probe, at best, if it was already sorted, we might have to go, well, you still have to go through the whole thing. If you were looking for the largest value, it would have to go to the end. Okay, on average, if you did a infinite number of searches, it would converge on, of random values. It'd be about half on average, okay? So let's say you had 1,000,000 elements in your array. On average of a large number of linear probes, you'd need to make 500,000 comparison checks to find what you're looking for. Well, in a binary search, we're at log 2 of n. A log 2 of 1,000,000 is approximately 20. By checking 20 values, you can always determine whether the thing you're looking at is in or not 1,000,000 items. And you can use 30 comparisons to check 1,000,000,000 things. So 40 will get you to 1,000,000,000,000, by the way. In 40 comparisons, you could have one database holding an identity of every human being on the entire planet and then some, right? There's only like 7 to 10 billion people on the planet. So you got 100 to 1 more people. You're searching 100 to 1 more elements than there are people on the planet if you go to what did I say, 40 comparisons. That's a huge gain, right? Well, let's look at some code. Or let's start with the same code that we had in our linear search example. I'm adding one more case down here because when we're sorted and we're using a binary search, we have to concern ourselves with the magnitude of what we're searching. As we'll see, this is the value of the last element in our test data array. These other ones are the same as they were before. Element number 4 is going to be the very first element in the array. This one here and that one there will be somewhere in the middle of our test array. This one will be a value that's not in there at all. The rest of this is the same as we saw before. We have another wrapper function. This is the same thing. I increase this because when we're searching for this giant number down here, I want to make sure it looks nice, but other than that, it's the same thing, and it calls bsearch instead of my linear search. So let's look at the bsearch function here. What does this do? Same thing. We got our array. These are all the elements. Here's how many elements have values that we want to search. This is the value we're looking for. All right. Now, as I explained with the cards, you set the low to the far left. That was the blue pen. You set the high to the total number -1. That's the very last element in the array. That was the black pen. Okay. So we simply always ask, is the low index always going to be less than or equal to the high index, right? The key here is to make sure you don't forget that equals, all right? Because when these two converge, if you search all the way to the end and you make all the possible comparisons before you find what you're looking for, these two will both be pointing at the same element, so you have to make sure that's in there. Okay, so what do? We calculate the middle, low plus high over 2. This is going to give you an integer value because we're assigning it to an integer data type. These two items right here are both integers anyway, as is the denominator. So the computer will not even use a floating point operation to do this, by the way, and that's what we call integer division when it calculates this and gives you the floor. Okay, so is the midpoint, that was the red pen as you recall, is that the one we're looking for? Because you're going to run into it quite often before you finish looking. If you have, then you found it, you just return it, and you're done. Is the thing I want on the left of that red pen, the middle point, is it less than the current midpoint? And if so, remember, down here, of course, it's not equal. And so what we're doing is we're saying, where are we going to look for the next one, right? So if the value I'm looking for is less than the current midpoint value, then we move the high pointer down because it can't be on the right. We need to make a new right end, and that would be mid minus 1 because we already checked the mid one, right? Otherwise, we know the value must be greater than because it's not equal, it's not less than, therefore it must be greater than. So we take the low index and we move it to the right of the midpoint by 1. The low one in the with the cards was the blue pen, you remember, okay? Go back to the top of our loop and we ask, did the pens cross, right? Are we to the point where it doesn't make sense anymore? And, if the answer is no, we get a new midpoint and we go on our merry way, just like we saw. If this process continues until the low pointer winds across the high pointer, or vice versa, the high pointer keeps moving to the left and crosses the low pointer, then this will no longer be true and we fall out of the while loop and cannot possibly find what we're looking for. Okay, let's compile this and let's run it. Let's have another look-see here. Remember, this is the same data we had in our linear search. So this is unsorted data, right? This is our sorted data. Do a double check here, right? There's this big number there. There's our, starts with a 4 like it did last time. WC minus L will tell us how many elements are in our test data set. Or more accurately, be careful about this. This is exactly how many lines of text there are in this file. If you're going to use this technique, understand you're counting lines of text. If there's 5 numbers on this line, it's not going to tell you the number of elements, the number of numbers. No, this literally means tell me the number of lines of text in this file. So don't misunderstand what's going on here. I purposely put one number on each line in this exact case. There's no blank lines so that I can actually do this to see how many there are, okay? So let's run it and give it our sorted data set. And I don't know what I'm doing. I called it binary. Okay, let's try that. It might work better if we name the file correctly, right? All right, what do we got here? It says it found a number 68 at 6. I could not find the 9999. 22 is at 4. 4 is at element 0. And this giant number is at 25. Well, if we have a total of 26 elements in our data set, the very last one has index number 25. The very first one would have element 0. That's our 4, and clearly we can see that's up here at the top. That worked out fine. 68 is at 6, and 22 is at number 4, right? So if this is 0, 1, 2, 3, there's number 4 right there. That works out 5, and 68 is on number 6. So our binary search works. Yay. Let's run it on a test data file that is not sorted. This will not work. Don't do this. Okay? And this is proof, right? I mean, logically, you can reason this out in your head, and you can see that it's not going to work. Why does it not work? Well, it doesn't work because when you're finding the middle in your data is sorted, let's say that happens to be the middle one, we know that every value over here must be less than 91, and every value over here is greater than 91. When it's unsorted and you pick the middle, and maybe it's this right here, what we're doing is we're suggesting that every single value over here must be less than 76. We're not going to look over there for a number like 82, okay, or 92, because if this is the midpoint, it's not supposed to be over there, okay? So make sure you use the right kind of data set in here. So that's what a binary search is. See you next time.